Okay, welcome students. Back to chapter 5, section 5.1. Okay, is on inner product spaces. Okay, so 5.1. Let's go up here. 5.1 is inner product spaces. Okay, so inner product spaces. Okay, let's go over kind of what we already should know about product spaces. They're not called product spaces in the math that comes before this. What they're called is basically dot product. Okay, and so this is how we multiply. One way to multiply two vectors together. Okay, so we're gonna launch off of what we know, which is the dot product, and then generalize that. We're gonna get more and more and more general. So we're gonna start specific, and then we're gonna do 3 more layers of general. Okay. So for vectors x and y, 2 arbitrary vectors in R3. Okay. 1, the dot product is defined as x dot y, which is equal to x1 y1 plus x2 y2 plus x3 y3. Okay. Okay, number 2, the magnitude of x is denoted these kind of double absolute value bars, which is equal to the square root of x dotted with itself. Okay, which is equal to the square root of x1 squared plus what? X2 squared plus x3 squared. Okay. Number 3. The cosine of theta is equal to, I'm going to drop this down a line. The cosine of theta, where theta is the angle between 2 vectors, is equal to x dot y over the magnitude of x times the magnitude of y. Okay. Once again, we should have seen this at some point. Okay. Okay, and this theta, where theta is an angle, is an angle between x and y such that 0 is less than or equal to theta, which is less than or equal to 180. Okay, so we're looking for an angle. We're looking for the minor angle, is what it's called, the minor arc. Okay, it's some angle between 0 and 180. Okay, number 4. If x dot y is equal to 0, okay, so if the dot product is equal to 0, then the angle between them, between x and y, is pi over 2, okay, or 90 degrees. This is referred to as orthogonal, which just means perpendicular. Because the cosine of 90 degrees is 0. Okay. Okay, so this is kind of more specific. Okay, so let's go a little bit more general. Let's go one step more general. Okay, so definition. Okay, so we'll say that this is specific. Okay. Definition. Okay, let x equal x1, x2, to x of n. So we're not going to restrict ourselves this time to just 3 dimensions. Okay. Okay, so and y is the same, has the same dimensions. y1, y2, to y sub n. Okay. So these are 2 vectors in R sub n. Okay. I'm going to write that. B, let these be vectors in Rn. Okay. We define the standard inner product in R sub n. Whoops. Bring that back. R sub n denoted as, okay, now we use the angle brackets. Okay. Angle bracket x, y. Okay. Okay, where xy, angle bracket xy is equal to x1, y1 plus x2, y2 plus plus xn, yn. Okay. The magnitude, we don't call the magnitude, we call it the norm now. The norm of x is still equal to the standard inner product of a vector and itself. Oops. Let's use those angle brackets. Okay, so standard inner product of a vector and itself, and then we square root that, and this just generalizes to x1 squared plus x2 squared plus dot 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 plus xn squared. So we can find the norm of an nth dimensional vector. Okay. Okay. Properties of standard inner product are as follows. Okay, 1. Okay. The inner product of a vector and itself is always greater than or equal to 0. Okay, furthermore, x, the standard inner product of x with x equals 0 if and only if x was the 0 vector. Okay. Had to have been the 0 vector to equal 0. Otherwise, it's positive. Okay, 2. The inner product of x with y is equal to the inner product of y with x. So the inner product is commutative. Okay, so the inner product is commutative. Okay, number 3. A constant times the inner product constant times the inner product is equal to okay, the constant times 1 of the values of the inner product is equal to x ky, but if you want to end up with kx ky, you would have to multiply k squared times the original inner product. Okay, and then number 4. Okay, the inner product of x plus y and then z is equal to the inner product of x and y, or sorry, x and z plus the inner product of y and z. Okay. So it's kind of like the inner product's variation of the distributive property, but it's kind of weird. So, okay, so this is more general, right? We took something that was now an nth dimensional, so we would say this is more general. Okay, we took our three-dimensional vectors and made them into made them into nth dimensional vectors. Okay. Now, let's go even more general than that. Okay, let's do a definition. Okay, we put here even more general. Okay, so let's do the definition here. Okay, move that over a little bit. Okay, so even more general. Well, what have we been talking about? We've been talking about, okay, vector spaces. So let V be a vector space okay, any mapping that associates each pair of vectors okay, U and V, vectors U and V now. These are vectors of a vector space. So way more general than just taking R sub n. Okay, this could be a bunch of other things. Okay, all the vector spaces that we've talked about before. Okay, is called, okay, that associates pair is called an inner product. Is called an inner product. Inner product in V provided the following hold. One, V inner product with V is greater than or equal to 0. Okay. Two, very similar to what we've been working with before. Okay, the V inner product with U okay, is equal to U inner product with V. Okay, 3, the inner product KU V is equal to K times the inner product of UV. Okay, and you could do that with, because it's commutative from above, you could do that with V as well. Just put V first. Okay, and then 4, okay, very similar to what we had before. Okay, U plus V dotted with, or dotted, inner product with W is equal to U inner product with W plus V inner product with W. Okay, and so that's even more general, right? So now we're saying that if these properties hold, then we're going to call it an inner product. Okay. Okay, so let's do an example with this. Okay, for our vector spaces. Okay. Okay, let's let's be example one. Okay, let V equal C naught, well, C exponent 0, AB, okay, and so this is zeroth derivative of, is it zero derivative or zero? Let V equals C. I don't think we've defined C naught yet. Yeah, I think we're defining it right now. So just, yeah, okay. Because if it doesn't have parentheses, so it's not derivative. Okay, and FG is an element of V. Define, okay, the inner space of F and G as equal to the integral from A to B, okay, of F of X times G of X dx. Okay. I don't think we necessarily define this as a vector space. Let me check real quick. We're doing vector spaces. Mhm. Mhm. Yeah, I don't think we, it might have been in the homework. I'd have to check the book. I don't think we defined that vector space particularly. Sure. The book, if you did not specifically do that vector space, otherwise I'll tell you which page it's on in the book. Doesn't look like it. Yeah. Okay. Was thinking that maybe they had done like an example with it, or where they're integrating this vector space. Yeah, but they don't. They don't do that. Okay. Okay. So here we go. It doesn't, it is C0. Okay, it is the derivatives. They don't need to have it in parentheses. In the book, they don't have it in parentheses, so I should have it in parentheses. Okay, so that is the zeroth derivative. Okay. It just means that it has zero derivatives. Okay, so we're gonna say that they're integrable. Okay, so we're gonna go backwards. Okay, so that is the zeroth derivative over the interval AB. Perfect. Okay. I was wondering, like, sure that the notation is correct. Okay, cool. Okay, so that is a vector space. Okay. Okay, and define this as the inner product is FG, how we defined it, and inner product. Okay, so it has to satisfy those four properties. Okay, so let's see if it satisfies the four properties. Okay, 1. Is F inner product with F equal to AB of f of x squared dx, okay, because that's what this would be. It would be f of x times f of x, so f of x squared dx. Is that greater than or equal to 0? Okay, so we're taking a function and we're squaring it, and then we take the integral of that. Well, any function squared is going to become a positive function, and any area under that positive function is going to be positive, so that works. Okay. What happens when I do 0 inner product with 0? Then I just get the integral from a to b of 0 dx, which is equal to 0. And so that checks as well. Okay, so we're good. We're good with that. Okay. Okay, number 2. Is f with g inner product the same as g inner product with f? Okay. And so does a to b f of x g of x dx equal the same thing as from a to b g of x f of x dx? And that does work. This is equal to, yeah, so that does check. Okay, number 3. Okay, is kf with inner product with g equal to k times f inner product with g? Okay, let's check this one out. Okay, this one is going to be a to b of k f of x g of x dx. I can pull the k out in front. That's k a to b of f of x g of x dx, which is equal to k times fg inner product. So that does check. And number 4, okay, is f plus g, okay, combined with a third vector h. Okay, what does this equal? Okay, let's see what this equals. So this is going to be the integral from a to b of f of x plus g of x dx. Okay, with h, right? With h. Okay, so that would be h of x dx, right? So I could distribute that h of x. So that's a to b of f of x h of x plus g of x h of x dx. And now I'm going to break this up into two separate integrals. A to b of f of x h of x dx plus integral a to b of g of x h of x dx. Right? Okay, so this is going to be equal to, by definition, okay, f, the inner product of f and h, plus the inner product of g and h, which is exactly what we wanted. Okay, so that checks. So yes, fg is an inner product in V. Okay, and this is actually has a special name. This this type of inner product. Okay, this is called the inner product of functions. This is called the inner product of functions. This integral, multiplying the functions and then taking the integral, is called the inner product of functions. Okay, this a to b of f of x, g of x, dx. That's the inner product of functions. Okay. Okay, cool. Okay, let's use this inner product of functions that we've defined. Okay, to do another example here. Determine the inner product absolute value of f or not absolute value of f, it's the the norm, sorry. Determine the inner product, the norm of f and the norm of g, okay, in, okay, okay, C naught okay, C naught okay, and between 0, 1 of f of x equals 8x and g of x is equal to x squared minus 1. Okay, so the inner product of f and g is equal to 0 to 1 of 8x times x squared minus 1. Okay, f of x and g of x dx. Okay, distribute the 8x, I get 8x cubed minus 8x, integrate 0 to 1 dx. And I get, this is going to be 8x to the 4th over 4 minus 8x squared over 2 from 0 to 1. And that's going to become 2 minus 4. So 2 minus 4, which is negative 2. Okay, what's the norm of f? That's going to be ff. Okay, the f with the inner product of itself. Okay. Okay. Which is the square root of, it's actually, the norm is equal to, sorry, it should be the square root of that, right? Let me just make sure I'm doing this correctly. Yes. Yes, it should be the square root of the inner product, sorry. Left off a square root. Okay, good. Okay. And so this is going to be the square root of the integral from 0 to 1 of 8x times 8x. Okay, this is equal to okay, the integral from 0 to 1 of 64x squared dx, okay, square root, which is going to be equal to, okay, 64x cubed over 3, evaluate from 0 to 1, square root it, okay, which is just 64 thirds. So this is equal to the square root of 64 thirds, which is equal to 8 over radical 3, which you can leave it like that if you want, or if you want to rationalize the denominator, that's 8 radical 3 over 3. Okay. Okay, what about g with g? Okay, the norm of g. Okay, let's do this one. The square root of 0 to 1 of x squared minus 1 times itself. Okay, that's going to be equal to the square root 0 to 1 of x to the fourth minus 2x squared plus 1 dx. Let's integrate this. Oops, and then evaluate. Okay, so this is going to become x to the fifth over 5 minus 2/3 x cubed plus x from 0 to 1. Okay, so this is 1/5 minus 2/3 plus 1. Okay, and so that's going to be 1 minus 2/3. I'll group these together first. That's 1/3. That's 1/5 plus 1/3, which is 8/15. So square root of 8/15, and then you could again rationalize it if you want. You would get a 2 radical 2 on top over radical 15. So we would get 2 radical 30 over 15 if we rationalized. But that's fine. Okay. Properties of the inner product. Let's look at some properties of the inner product. Properties of the inner product. Okay, 1. Okay, UV is less than or equal to absolute value U, or not, I keep saying absolute value, the norm of U, the absolute value of the inner product, okay, is less than or equal to the norm of U times the norm of V. Okay, and this is called the Cauchy-Schwarz inequality. This is the Cauchy-Schwarz inequality. It's kind of like the triangle inequality. Okay. Okay, it's similar to another famous inequality. Okay, called the triangle inequality. Triangle inequality. okay, which is the magnitude of u plus v, okay, is less than or equal to the magnitude of u plus the magnitude of v, okay, so that's called the triangle inequality, okay, which holds true for vectors because of the Cauchy-Schwarz inequality. Okay, number 2. The cosine of theta is equal to the inner product of u and v angle bracket over the magnitude of u, magnitude of v, okay, where u and v occur in a real inner space, okay? V occur in a real, maybe I should put valued inner space when we're using real numbers. Okay, no complex numbers. Real inner space. Okay. Okay, 3. Determine the angle determine the angle between the two functions okay, f of x equals sine x and g of x equals cosine x. We're going to find the angle between these functions on, we'll do negative pi to pi. Okay, so what's the angle between the functions of sine and cosine? On negative pi to pi. So let's use our inner product, our inner product for functions. Choose our inner product for functions of f and g equaling negative pi to pi of sine x cosine x dx. Okay, and that is equal to sine squared x over 2 negative pi to pi is equal to 0 minus 0, which is equal to 0. Okay, so I could do a u sub on this. If I let u equal sine, then du is equal to cosine x dx, and so it makes it real easy to see that the u is going to become u squared over 2. And then I just plug in my sine x for u, and I get sine of pi is 0, sine negative pi is 0, and it goes to 0. So between negative pi and pi, okay, so because the cosine of theta is equal to uv, the inner product of uv over the magnitude of u magnitude v, well, we know that the inner product of f and g was 0. And so it doesn't matter what the magnitude of u and the magnitude of v are, it's going to go to 0. And so the angle between them, theta, had to be pi over 2. Okay, therefore, the functions cosine x and sine x are orthogonal between negative pi and pi. Okay. Okay. Let's change gears now and see what would happen if we introduced complex numbers. Okay. If v is a vector in Cn, okay, nth dimensional complex numbers, and then we denote v, v bar, as the complex conjugate of v. Okay, so the complex conjugate of v. Okay, in C2, that would look like in 2 dimensions, C2, that would be a plus bi, a minus bi. Okay. So let's see one. I think that's just C1 actually. That's just C1. Okay. So yeah, that's C1. C1, remember that a complex conjugate, I'll just write it. This thing ever decides to erase. Okay. So in C1, complex conjugate is a plus bi, a minus bi. So that's what complex conjugate means. It means you take the complex number, and if it was a positive, then then it becomes a negative, a minus sign, and vice versa. Okay, so we would say that these are complex conjugates. Okay, if we had C2, then now we'd have 2 of those, and then we'd have to get the conjugates of both components of the vector. Okay, so let's do a definition. Okay, if u and v are vectors in Cn, we define the standard inner product okay, as a UV okay, the inner product UV equal to U1 V1 conjugate plus U2 V2 conjugate plus dot 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 plus UN VN conjugate. So we're constantly taking the conjugate and basically dot producting that. Okay, each of the components of the vectors. Okay, so definition, let's do a definition. Okay, and this is going to be the most general. Okay, most general, right? Because we dealt with real, with three-dimensional real values. Then we upped it to multi-dimensional real values. Then we upped it to vector spaces. Now we're upping it to complex, okay, inner spaces. Okay, and so if it was a complex, this is kind of the most general. Okay, so if it's a complex inner space, okay, let V be a real or complex. If the numbers are real numbers, then it just this becomes kind of trivial because the conjugate of a real number is a real number. Okay, it's just unless you have a complex component, an imaginary component, you don't really have a conjugate. Okay, because again, we go back to a plus bi and a minus bi. What's the conjugate of just a? Well, it's a. Okay, so again, we're kind of going back to the broadest definition here. Okay, so let V be a real or complex vector space. Okay, but we're gonna make sure that we are able to define this for complex numbers. A mapping that associates with each pair of vectors UV in a vector space in a vector space V a scalar mapping that associates with each pair of vectors UV in a vector a scalar okay it denoted UV noted UV. Is this right? Let me go to the book real quick, make sure the definition is correct. I'm sure it is. I'm pretty sure I copied it right out of the book. But why are they calling it a scalar? Scalar, yeah, no, that's right. Okay, it says a mapping that associates these pair of vectors in V, a scalar denoted UV is called Okay, an inner product in V. Okay, so there's, I guess they're just calling this inner product a scalar. That's the most general term. Okay. Okay, inner product in V. Provided it satisfies the following properties. Properties. Here, one. VV, okay, V inner product with V is greater than or equal to 0. And, oops, come on, erase. Okay, and V equals 0. Okay, the inner product of V with V equals 0 if and only if V is equal to 0. Okay, 0 vector. Okay, next. Okay, number 2. VU is equal to, okay, the conjugate of UV. Conjugate of UV. Okay, so in this case, it's the conjugate of UV. Okay, equals UV if it's real. However, if it's complex, then it equals UV conjugate. Okay, so we would take and we would do the inner product on UV, and then we would take the conjugate of the result. Okay, number 3. KU V is equal to KUV. Okay, and 4. Okay. And 4 U plus VW. I should probably be putting vectors on all these things, but you get the idea. Okay, UVW is equal to UW plus VW. UW plus V. Why my U's and W's look similar? Okay, the norm. And again, this is the most general. Okay. And the norm is defined the same. Norm of V is equal to the square root of VV. Okay, V inner product with V. So it would be V basically dotted with its conjugate. Okay. So we were to multiply that out. Let's do this. Okay, let's find u dot v and v dot v. Okay, inner product uv and inner product vv, given a couple of complex numbers. So number 4. Okay, given, this is in C3, u is equal to 5 minus I, negative 3I, and 6 plus 2I, and v is equal to 3, 2I, negative 1 minus 4I. Okay, find uv, inner product uv, and the norm of v. Okay, given those two vectors, let's find the inner product and the norm. Okay, okay, so uv inner product is going to be equal to u1 v conjugate 1 plus u2 v conjugate 2 plus u3 v conjugate 3. Okay, so we're going to basically dot this, do the dot product, but with all the conjugates of v. Okay. Okay, so u1 is 5 minus I. What's v conjugate? Well, v1, what's v conjugate 1? Well, v1 is 3. And so that would be 3 plus 0I and 3 minus 0I, which is still 3. Okay, so the conjugate of a real number is just a real number. Okay, what about the next one? This is negative 3I, which is u2, and then v conjugate. Well, that's 2I, and so the conjugate is negative 2I. It's really 0 minus 2I. Okay, and then u3 is going to be 5 minus I times I'm sorry, not 5 minus I. It's 6 plus 2I. Lag. 6 plus 2I times, okay, and then this is negative 1 minus 4I. Well, what's the conjugate of negative 1 minus 4I? It's negative 1 plus 4I. Okay. Okay, so now I'm going to distribute. This is 15 minus 3I plus, this is 6I squared. Okay, this is going to be plus 6 times negative 1. I have to FOIL this out. This is negative 6 plus 24I plus negative 2I plus 8I squared. Okay. So this is going to be equal to 15 minus 3I plus I squared is negative 1, so that's 6 times negative 1 plus negative 6 plus 24I plus negative 2I plus 8 times negative 1. Okay. So I'm going to get 15 minus 3I. Okay, this is negative 6 and negative 6 is negative 12 plus negative 12. 24I minus 2I, I'm going to combine these and combine these, is 22I, and then negative 8 minus 8. Okay, and so I get 15 minus 12 is 3. 3 minus 8 is negative 5. Negative 3 and 22 is it a positive 24? Yes. Yeah, positive 19i. Perfect. Okay, and that would be the inner product of UV for this complex number. Okay, let's do call that A. Let's do the magnitude of V. Well, the magnitude of V is just going to be V inner product of V square root, right? Okay, that's the magnitude of V. Maybe I should have put that down. Okay, so V, the magnitude of V is equal to, okay, the square root of V1 V conjugate 1 plus V2 V conjugate 2 plus V3 V conjugate 3. Okay. So V in this case is 3, 2i, and negative 1. Okay, so this is going to be 3 times 3 plus 2i times negative 2i plus negative 1 minus 4i times negative 1 plus 4i. Okay, square root that. Okay, and so we get 9 minus 4i squared plus, okay, this is the difference of two squares. And so this is going to be plus 1 minus 4i squared. Okay, negative 1 squared minus 4i squared. Okay, because the middle terms would drop out. Square root. This is going to be 9 plus 4, because I squared is negative 1. Okay, plus 1 minus 4 times I squared. That's minus 4 times negative 1. So that's another plus 4. So everything's being added. So this is 9 and 1 and 4 and 4, which is 6, which is sorry, this would be 16. I'm sorry, because we have the 4 squared. Okay, and then I squared would be negative 1. It's negative 4 squared and then I squared. Yeah, negative 1. Okay, and then so that is plus 16. So this is 13, 14 plus 16, which is the square root of 30. Okay, that's the solution. Okay, so that's 5.1, and I'll see you in the next video.